What's up, guys? Welcome back to another Algebra 2 instructional video here with Mr. Gaines as we focus on section QF.3, which is the analytic parabola. So hopefully at this point you have taken a look at the kind of introductory video that I posted there about the Newtonian telescope. What the Newtonian telescope gives us is one example of a real-life application for a parabola, a three-dimensional parabola. And when we build parabolas, we sometimes build them with quadratic functions, as we have looked at in the section QF2, but more often we start looking at the analytic parabola, where we start to incorporate things such as the focus and the directrix to create this curve. So let's start with the definition of a parabola, because we've been throwing this term around, we've been looking at graphs of parabolas, but we haven't really dissected what a parabola means. So a parabola is the set of all points equidistant from a fixed point, a stationary point known as the focus, and a fixed or a set line known as the directrix. So if I take a look at this example over here, let's view this example over here on the right. This blue line is a parabola. The fixed point would be this point F here that we call the focus. The fixed line for this is not shown in the picture, but it would be some horizontal line. If we labeled it down here, we could call this line D. This line would be the directrix. So the focus is a fixed point inside the parabola. A directrix is a fixed line outside of the parabola. All points of the parabola are equidistant from both the focus and the directrix at all times. Now, how that related to the Newtonian telescope. The telescope works because light comes in and bounces off this parabolic mirror. So you can see down here at the bottom, this is a parabola-shaped mirror. And so the light's going to come in here at any angle, and it's going to reflect off that mirror. And no matter the angle, it's going to come to this centralized focus. So we can see that better here shown over in the graph on the right. As light comes in, it bounces off of the mirror and comes to the focus. And no matter what angle it comes in, it bounces at a different angle outgoing from the parabola, and all of these points end up at the focus. So what happens is the light comes in, it reflects to this mirror where you can see by looking through the eyepiece, and it magnifies the rays of light to magnify the image that the telescope is pointed at. So this is one of the real life examples that we can use a parabola here. In this case, a parabolic dish as we rotate it 360 degrees, but it's all derived from this idea of a parabola. So we use the definition of a focus and a directrix to actually come up with the equation of a parabola. So let's derive the equation for a parabola. So let's say I have some focus, and let's call this point F. And we're going to put this, here's the x-axis, here's the y-axis. And just to make this a little bit easier, we're going to put the focus at 0 on the x-axis. And let's call this point or distance D on the y-axis. So the focus is going to be at 0, D. Now there's going to be some type of parabola here, and it's going to go around this focus. It's going to be a rough sketch. It's not going to be perfect. But let's let this parabola start at the origin. I can do a little better than that. So it's going to have a vertex of 0, 0. And then there's also, again, from the definition, there's a directrix. So again, the definition says all points are equidistant from the focus and the directrix. So let me move this focus up just a little bit to make that a little closer to accurate. So if the focus is up D units from 0, 0 to 0, D, the directrix is down D units. So the directrix is a horizontal line. So this would be y equals negative D. So according to the definition, any point on this line is equidistant from the focus and the directrix. So again, this is not drawn to scale, but let me put a point on here. Let's call this point P. So then the distance from P to F, let's draw this segment here, is the same as the distance from P to the directrix, and let's make this a point D. Again, not drawn to scale. So P to F is equal to P to D. This is notation you've seen from geometry here. So those segments are the same length. Now we don't know where P is at necessarily. So let's say that it is any X coordinate and it's any Y coordinate that exists on the parabola. So it doesn't matter where along this parabola. I could put P anywhere here. It's going to have an X coordinate. It's going to have a Y coordinate. Then D is directly underneath P. So it's going to have the same X coordinate, but it's on the line for the directrix of y equals negative d, so its y coordinate is negative d. So what I want to do here is I want to use this equation, or this definition of a parabola, to derive the equation for the parabola. PF is equal to PD. Now let's go back a little bit to geometry or algebra 1. Anytime you want to find the distance of something that has coordinates, you guys can use the distance formula. So you might remember this. The distance formula is x2 minus x1 quantity squared plus y2 minus y1 quantity squared. So PF. Let's use the distance formula for P and F. I'm going to switch colors here. So PF is the square root of my x coordinates for P and F are x and 0. So x minus 0 would just be x. So x squared plus my y coordinates for PF are y and d. So I'd substitute those here in the distance formula. So this would be y minus d quantity squared, and we'll come back to that. Now for PD, here I have the square root of my x coordinates are x and x. So x minus x would just be 0, and 0 squared is 0. So I don't need anything in there for the x's for PD, because again, the x's would subtract to 0. I do need the y's. This would be y minus negative d, which is y plus d quantity squared. So this is a representation. This is an equation for my parabola. Now we want to simplify this equation. So what I'm going to do here is I'm going to simplify this equation, noticing that both sides have a square root. I'm going to square both sides. So if I square both sides, that's going to leave me x squared plus y minus d quantity squared equal to y plus d quantity squared. Now I'm going to multiply out these sides. So x squared is going to stay the same. If I square y minus d, I would get a y squared, and I would get d squared, but I'd also get minus 2dy. So I'd have x squared plus y squared minus 2dy plus d squared. On the other side of the equation, I just have to square y plus d. So that would give me y squared plus 2dy plus d squared. Now, I may notice that some of these terms are the same on the left side of the equation as they are on the right side of the equation. And remember, with most equations, we try to get y by itself. So what I'm going to do here is I'm going to move all of the y pieces over to the left side of the equation. I'm going to move everything else to the right side of the equation to get the y's on one side and everything else to the other. So I'm going to subtract y squared, and these guys are going to cancel each other out. I'm going to subtract 2dy. Those will not cancel out. Those would simplify to a negative 4dy. Then I'm going to subtract d squared to move it to the other side of the equation. And these will cancel each other out. I'm going to subtract x squared to move it over, and there's nothing to subtract x squared from over here, so it's just going to be a negative x squared. Now I'm close. If I want to get y by itself, I can divide here by a negative 4d. Those would cancel out. Divide this by a negative 4d. And I'm going to write it as a fraction here. So this would end up being 1 over 4d times x squared. So the equation for this parabola is y equals 1 over 4d times x squared. Now notice what d is. D is the distance from the focus to the vertex, which is also the same as the distance from the vertex to the directrix. So this is saying my equation is 1 over 4 d, where d is the distance from the focus to the directrix, sorry, from the focus to the vertex, or the vertex to the directrix, times x squared. This is the equation for the parabola here, the analytic parabola here, where the vertex is at 0, 0. Notice also that this is a vertical parabola. So this is a vertical parabola with vertex 0, 0. And that matches the graph given here. Now, remember with transformations, we can transform graphs. So when we transform graphs, we have different kind of shifts and reflections and things of that nature. Remember what we did with the vertex form of a parabola. When you shift left and right, up and down, that changes the vertex. So we can put some shifts into this and include this as y equals negative 1 over 4d times the quantity x minus h squared plus k. We should be familiar with this notation. This is a vertical parabola with vertex hk. So it's basically what we saw above, but now I have the ability to shift my vertex around. And this is going to be very key for us. So I'm going to go ahead and put a box around that. Actually, I'm going to take that box away. I'll give you a sketch here. So let's say then this parabola moved to the right and it moved up. So now we have vertex here that's hk. Let's say we have the focus here that is still h, but now it's k plus d, because remember, d is the distance from the vertex to the focus. Also the distance from the vertex to the directrix. So let's say the directrix is here at y equals k minus d. And some of that will probably make a little bit more sense when we start throwing in some numbers with this. But this is a form of the parabola that we're going to want to remember. It's going to give us some shortcuts later on. Now, we can also have a horizontal parabola. So these are examples where the parabola was vertical. A horizontal parabola would follow the equation that we have above, but we'd switch the x with the y. And so we're only going to see in this class, we're only going to see horizontal parabolas with a vertex of 0, 0. So x would equal 1 over 4d times the quantity, times y squared. And this again is a horizontal parabola with vertex 0, 0. So this would look pretty much the same, except for it would be a rotation of the parabola that we saw before. So my vertex is at 0, 0. It's a parabola that's going to open horizontally. So vertex 0, 0. I'm going to have a focus. This time my focus, the x coordinate is going to change. So let's make this d, 0. D being the distance between the focus and the vertex. And then that would make my directrix x equals negative d. So d units to the left. So these are the three equations that we are going to focus on here. This is the analytic version of a parabola. It allows us to find or graph a parabola with respect to the directrix, the focus, and the vertex. So let's go ahead and take a look. I know there's kind of a lot going on here. Let's go ahead and take a look at how these equations work with some actual numbers. So in problem 1, it says for each of the following, find the vertex, axis of symmetry, focus, and directrix for the parabola defined by the equation. Then sketch the graph, including each of the key features. So basically what we want to do is we want to take the equation that they gave us and make it look like one of these. So the first thing that we may notice here is when the x value is being squared, we have a vertical parabola. Those are what we're used to seeing with quadratics. When the y squared value is being, or when the y value is being squared, we have a horizontal parabola. This we're not used to seeing because it's not a function. This is not a quadratic function, but it still is a parabola. It still maintains the same definition, it's just turned to the side. So what I may see here in problem 1 is that y squared, the y is being squared. So what I know right now is I have a horizontal parabola. Anytime the y is squared, it's horizontal. Anytime the x is squared, it's vertical. So what I want to do is I want to get x by itself. So I'm going to divide by -4. If I divide by -4, now I'm going to rewrite with x to the left. So x equals -1/4 y squared. And so now I have x by itself. I have this in the form that is ready to give key features of my parabola. What I may notice here is for the vertex, we're looking for shifts. If you notice this form, there's no shifts. So the vertex is at 0, 0. And I'm going to go ahead, I'm going to come down, or actually I'm going to go up over here to the right, and I'm going to sketch this at the same time. So there's my vertex, and I've labeled it with 0, 0. Now, to find the axis of symmetry, the axis of symmetry goes through the vertex, always through the vertex. And because it's horizontal, it's either going to go to the left or to the right. Now, what we may notice here is that we have a -1/4, a leading coefficient of negative. So what this is going to do is it's going to reflect the parabola. Now notice that this value when we looked at the equation was positive, so it opened to the right. If the negative is in front of the y value, it's going to open to the left. So my axis of symmetry is actually this dashed line here, which is y equals 0. So I will just label this as axis of symmetry. It's y equals 0. It is the x-axis. Now we need to find the focus and the directrix and then sketch in the parabola. The focus and the directrix go back to the definition. They're the same distance from the vertex. So I know where my vertex is. Focus and directrix are the same distance on either side of my focus and directrix. Notice that the focus is always inside the parabola. So it's on the axis of symmetry, and it's inside the parabola, and it is d units away from the vertex. So with our equation here, x is equal to 1/4 d y squared. That's the generic equation. So I know my focus has to be on this axis of symmetry. It's over here to the left of the vertex. It is d units left of the vertex. Well, what is d? D comes from this part of the equation. My leading coefficient, 1/4d, has to equal -1/4. Sorry, -1/4. So if I want to solve this, you could probably find this answer out already. But if I want to solve this algebraically, I would cross multiply. I would get -4d equals 4, and I would divide by -4, so d would be -1. D technically is an absolute value, so d is technically 1. But if you want to list this as -1, that's okay as well. What this tells me is my focus is 1 unit away from my vertex, and we know it's on the axis of symmetry. It's to the left. So my focus is going to be at -1, 0. Now my directrix is going to be the same distance away, but it's going to be on the other side. So notice that the directrix is outside of the parabola in all of these cases. So it's going to be 1 unit away from the vertex, but to the right. And this would be a vertical line. So let me extend my axis here. This would be at x equals 1. So now I have my focus, my directrix, and my axis of symmetry. So now we can draw on the graph. So all points should be equidistant from the focus and the axis of symmetry. So we want to draw in a sketch that's going to represent that. It doesn't have to be perfect. And there we have one that kind of represents the U shape around the focus, where all points are equidistant from the focus and the directrix. So what we're doing here is we're rewriting this equation into a form that matches one of the equations that we saw above. And then we can go ahead and find our values, our vertex, our focus, our directrix, and our axis of symmetry, and sketch a graph. Let's go ahead and take a look at 1B. So there I have all my key features labeled, and I have a graph. I'm ready to start getting those, finding those pieces and putting those in the right locations. So first thing that I want to do is I want to identify if this is going to be a horizontal or a vertical parabola. So I can see here that the x is being squared. I'm going to get the y by itself, and when y is by itself, it is a vertical parabola. So I'm going to divide by 12 here, and I'm going to write this as a fraction with y to the left. So y is equal to 1 over 12 x squared. So what I can see here is that there are no shifts to the left or to the right. So my vertex is 0, 0. My axis of symmetry has to be on or going through my vertex. Now this parabola, if I go back here and look at our equation, it's a positive leading coefficient. So this parabola is going to open up. My axis of symmetry is going to be through the line x equals 0 because it is a vertical line. My focus and directrix are where I have to find the different pieces. So remember that back to the generic equation, y is equal to 1 over 4d times x squared. Essentially, the absolute value of a is equal to 1 over 4d. So we've already labeled a as our leading coefficient, our dilation factor. That's going to be equal to 1 over 4d. So that means 1 over 12 is equal to 1 over 4d. If you can solve this quickly, that's fine. If you need to cross multiply, you get 4d equal to 12. And you divide by 4. So d is equal to 3. So what I would do is I would move up 3 units. It's 1, 2, 3. I'll just go ahead and sketch those on the graph here. And this is my focus. Label this point as F and this point as V. So my focus F would be at 0, 3. My directrix would be 3 units down from the vertex, 1, 2, 3. So my directrix would be a horizontal line. Let's try to make it actually go through that value. There we go. Horizontal line where y is equal to -3. And from here, now I can sketch in my curve. So again, that curve doesn't have to be perfect, but we want to make it look a little bit more like a U shape than a V shape. And as long as we have our correct labels in there, then we're good. So our vertex is at 0, 0. Our directrix at y equals -3, a focus 0, 3, and then my axis of symmetry at x equals 0. So here we have an example of a vertical parabola and a horizontal parabola that we can create and we can graph using the analytic definition of a parabola. This is a great place for us to stop. When we continue with part 2 of this video, we're going to look at a little bit more complicated versions of these equations, start looking at some shifts, some horizontal and vertical shifts, and then we're going to look at how we can derive the equation of a parabola given different information. As always, thank you guys for tuning in, and I'll see you soon.